Okay, hello everyone. Today we will be talking about kinetics. The topics that we will be going over in this videos include stoichiometry, sorry for my bad spelling, and Rayleigh law, reaction mechanism, Maxwell-Boltzmann curve, integrated Rayleigh law, and half-life. And let's begin by talking about what is chemical kinetic. Chemical kinetic is study of changing rate of reactions under various conditions, such as temperature and pressure, and molecules events that take place during the reactions. Some of the factors that you need to remember, which will change the speed of the reactions, include temperature, surface area, concentration, and catalyst. So if any of those increase, the speed of the reaction will also increase. Now let's talking about some of the basic stoichiometry that you need to know for the related rate law. No, sorry, not the rate law, just consumption rate and the production rate. Basically, the stoichiometry states that the speed of a reactant being used up or a product that's being produced is related to one another. Let's take a look at this example. This example is a ammonia and oxygen being react. We are given the consumption rate of ammonia, and we need to find the consumption rate of oxygen and the formation rate of water vapor. So here we can use our stoichiometry. We are given the consumption rate of ammonia. If we divide it by the coefficients that are different and then multiply whatever is the thing that we want to find. For example, this one, oxygen, we multiply the coefficient of oxygen. We get this ratio 5/4, and then we multiply the rate of consumption of ammonia. We plug in the number and we can calculate the rate of consumption of oxygen also. Great. Similarly, we can also do this for products. If we divide the coefficient of ammonia and then multiply the coefficient of water, and we multiply the rate of consumption of ammonia, we get the rate of formation of water. So it's pretty simple, just like what you did in grade 11, except we are now just dealing with the speed that's something is being consumed or something being produced. So another type of question that you might be seeing in the AP exam may ask you the rate of consumption or production of something, but now it gives you the mass rate of consumption. So what you need to do is just convert this into the change of concentration by dividing the molar mass. So in this case, we got sodium hydrogen carbonate. We got the rate of change of the mass. Then we divide the molar mass of this compound. We get the rate of the change of this compound, the sodium hydrogen carbonate. And then we can use this to do our stoichiometry. And we just did what we did last page. We first divide the coefficient of the compound, then multiply the one that we want to get, which is 1. And then if we want to get the mass consumption rate of something, now we just simply multiply by the molar mass, and we get the mass consumption rate or the production rate if you are dealing with a product, not a reactant. Now let's talk about what is the rate law. This is the most important topic of the whole chapter. And let's begin by the definition. A rate law for a reaction is it express the way that the concentration of the reaction affect the rate of reactions. Yeah, a lot of words, but basically if you got a reaction like this, we don't care about products, and if the reactant A has coefficient of A and reactant B has a coefficient of B, then we can write the rate, the speed of the reactions, into form like this. A, B, C, they are the reactants, and A, B, C, they are the coefficients, and the K is just some kind of constant. So one thing to keep in mind is that this is our rate law by default. If the question doesn't mention anything, you may just assume the rate law is like this. Otherwise, the rate law may not be the same as the default one. You have to experimentally determine what is the actual rate law. So it might be different, but you can assume this by default if the question just didn't say anything. Now let's talking about what is order. So in this case, rate equals to K blah 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 blah. We can call that this reaction is A order with respect to A and B order with respect to B. Okay, kind of confusing, but you will be understanding that once we see the example. Basically, we are just looking at the power of a specific type of reactant. In this case, the rate has nothing to do with the reactant A, and A has a power of 0, so we call this reaction is 0 order with respect to A. But here, this is A to the power of 1, so we call this first order with respect to A. And similarly, this is power of 2, we call this second order with respect to A. And just give you a quick example. So this reactions, by default, we might assume that the rate law is like this. K is a constant and Hi to the power of 2 because it has a coefficient of the 2 at the front. And we call this reaction is second order with respect to Hi. Now let's talking about how to determine the unit of K, which is aka the rate constant. By default, the rate has a unit of a molar concentration per second, and the concentration has a unit of m, the molar concentration unit, and the K is what we need to determine and what we don't need to know. What we don't know, sorry, that it has to be able to balancing the two sides of the equation. And let's see the basic derivation of the unit of K in 0, first and second order reactions. So here, we plug in that rate is equal to m over s, and the K is just something that we need to find. And here we can see that K is directly equal to the unit of rate. In the first order, we now have the concentration of a certain reactant. So here we plug in the unit of rate as usual, and the K and the unit for the concentration of this, which is just m. And we put K to the other side, and we have this divided by this. And then m cancel out, and K is just per second in the first order. For the second order, we do the same thing, and the rate is m over s, and now it has a power of 2, or we can say A has a order of 2, and we plug in m to the power of 2, and we have this divided by this, and we got unit is 1 over m times s. And yeah, if you don't remember, m is simply equals to 1 moles over 1 liter. That's the molar concentration unit. And we just can also convert m into this form, moles per liter. And here m is the bottom, we just flip it. As mentioned before, the rate law has to be experimentally determined. We need to analyze the experimental data in order to get the exact rate law. And that's what this chapter is for. And we need to analyze the experimental data and calculate the rate law by hand instead of looking at the reaction itself. If you are given a table of different trials with the concentration of each reactant and the rate, you can pretty much ignore the reaction because that's going to be completely useless. This one is not going to help us determine the rate law. And just a quick recap that a rate law has a form of this. If we sub in the data that's inside our table, we get 3 different equations with 3 different variables, K, A, and B. In the first step, we will be looking for 2 trials where the concentration of all the reactants are the same except one column. In this example, we can see that in trial 2 and 1, the concentration of fluorine is different, but the ClO2 are the same. And also in trial 1-3, the ClO2 are different, but the fluorine is the same. If we use trial 1 and 2, we divide the first equation by the second equation, and we can cancel out a lot of terms. That's why we always pick the 2 trials that has a lot of similarity except one reactants being different. That's why we can cancel out K and K and the concentration of B and B. And in this case, the fluorine has a concentration that's different. And we have 1 over... Okay, let me move this up a little bit. And we can see that the concentration of fluorine has a power of A, and the other side is the ratio of the rates in 2 different trials. And we can immediately see that A equals to 1. So we solve one of the variable, and we now apply the similar technique to solve for B. And this time we cancel out the concentration of fluorine and the rate constant, and we take the ratio of the rate of trial 1 and 3. Now we get a very similar situation, and we got B equals to 1 just by looking at this. And now we get the rate law. The only thing left for us to do is to determine the rate constant K. That part is going to be very easy. You can pick any of the trials that's inside the table and just sub in the value once you get the entire rate law function. And you sub in the value and you just solve for K. And don't forget to put the proper unit at the end of your value. And we have already gone over how to determine the unit. Just take a look at a very similar example. Again, we are given a table of trials with different entries like the concentration and the rate. And first, we're looking for the trials that has a lot in similar. In this case, I first pick trial 1 and trial 2, and I get a ratio of the rate in each of the trials. I got 1 over 4. And the other one, I got the concentration of B. And now we can just see that B equals to 2. If this is not like a very nice number, you can just use your calculator and do some logarithmetics. It's also very easy. And now I pick trial 1 and 3. Now we determine the ratio of the rates in 2 trials, and we also determine the ratio of the concentration of A in 2 trials. And we have 1 over 2 to the power of A equals to 1 over 8. And we solve for the value of A, and we obtain the rate law. For time reason, I'm not going to be calculating the rate constant K, because this is very easy. You just plug in the value and calculate it using any one of those trials. Now let's take a look at an example where the data is not that ideal. And now what do? So first, we try to get whatever we can for now. We divided 1 by trial 2, trial 1 by trial 2. And we immediately cancel out the concentration of B and the rate constant of the reaction. And then we get the ratio of the rate and the concentration of A. And we easily get that A equals to 1. But if we observe the table carefully, we can see that there's no two trials where the concentration of A is the same, but the B is different. The concentration of A is always different. Don't panic. In this case, what we can do is 1 divided by trial 1 divided by trial 3. We get the ratio of the rates in 2 trials. We cancel out the K just like what we did before, and we have the ratio of concentration of A. But one thing to note now is we already get the value of A, which we can evaluate this term instead of just trying to cancel this out. And just like before, the ratio of B, we are waiting to solve the variable B. And here we multiply the equation by 4 on each side, and we are being left with this expression over here. And we solve that B equals to 1 also, and we obtain the rate law. So this part is quite important, and how long did you practice decides that how much time do you really need to solve these kind of problems during the real exam. So I suggest that you can do some more practice to make sure that you get a hang of it. Next, let's talk about reaction mechanism. According to reaction mechanism, the rate law is directly proportional to the effective collisions between the molecules. The effective collision requires correct orientation of the reactant molecules. And the second thing is that the molecules must contain sufficient energy to make this collision effective. Now let's talk about orientation. So if we are looking at a reaction like this, and we know that the molecules are looking like this, again, you're gonna be given how does the molecules looks like in the AP exam. So you don't need to worry about that. You don't need to memorize it. Now let's talk about those two scenarios of different collisions. In first case, we can see that B and B are going to have a head-on collision, and which going to give us the correct orientation of these molecules over here. But imagine if they are moving like this and having a collision, they're gonna end up have something like this, which is not valid. So this collision doesn't have the correct orientation. The second thing is to have sufficient energy. During a collision, the particles must possess minimum energy threshold for a successful reaction collision. And that minimum energy threshold is called the activation energy, denoted by E followed by a letter A subscript. And this model is called Maxwell-Boltzmann curve, and it's showing you the distribution of the kinetic energy of the molecules that's participating in the reaction. Let's take a look at the basics of the Maxwell-Boltzmann curve. The x-axis is going to be the amount of kinetic energy of a certain molecule, and on the y-axis is going to be the percentage of the molecules where the reaction is taking place that contains a certain amount of kinetic energy. And here you can see two different dash lines. So the highest point, the peak over here, this distance is called the average kinetic energy, Ke, of the reaction. That's saying how the average kinetic energy that I'm expecting to get of this reaction model. And the activation energy is the minimum energy threshold for a particle to make a successful collision. And we can see that in this area, in the shaded area, those particles will be having successful collision, whereas if the other molecule collides, they will not be having a effective collision. Therefore, they will be just doing nothing. And those are the particles that are participating in the collisions. As the temperature increases, the kinetic energy of the reactions particles are being increased. The peaks will be lower and the graph will shift to the right. And you need to remember how does the graph of Maxwell-Boltzmann curve shift as the temperature increase. So here I'm giving you three different curves at three different temperatures. The T1, the graph 1 has the lowest temperature, and the graph 3 has the highest temperature, and the graph number 2 is in the middle. We can see that the peak of each graph is becoming slightly lower as the temperature increases, and also the peak is also shifting towards the right. And during each shift, we can see that more percentage of molecules will possess enough energy to make successful collision, as denoted in this shaded area. And you just need to remember this pattern and you will be fine for the AP exam. And one thing to mention is that the activation energy is how much energy that you require, and it doesn't really change as the temperature increase, because the increase in temperature only increases the kinetic energy, but it doesn't really change the requirement of how much energy you need for the successful collision. And similar patterns can be used to model the distribution of speed with molar mass of different molecules. So here we can see there's three different molecules. Assuming that they have the same temperature, that's how their speed distribution looks like. So here, oxygen has the maximum molar mass among the three, whereas the hydrogen has the lowest molar mass among the three. And it also shifts like how the temperature shifting the kinetic energy. One thing to keep in mind is that at the same temperature, it means that they have the same average kinetic energy, but the lighter molecules get higher speed distribution. We can see that for hydrogen, there are more molecules that has higher speed, and the oxygen, it has the greater molar mass. Therefore, it has the least amount of molecules that possess high speed. And now let's talk about the factors that change the rate and how do they affect the rate change. The concentration gives more molecules during a reaction. That means more collision frequencies. So it means more the higher rate, and this means that the reaction will take place faster. Temperature, as we have discussed before, the high temperature is going to give the molecules higher kinetic energy, which gives more molecules sufficient energy to make successful collisions. And And the catalyst is going to decrease the activation energy, which is the energy that we require to make a successful collision, by providing a alternating path for the reaction, which we will be talking about this soon. Let's talk about catalyst. Catalyst is a substance that speeds up the rate of the reaction without itself undergo a permanent change. In other words, it first shows up in the reactant side of a reaction, and then at the end it will show up in the product side of the reactants. So it goes in and it goes out. And let's take a look at our old friend, the potential energy graph. And the activation energy for the forward reaction is EA1, and the EA2 is the backward reaction activation energy. And let's take a look at the effect of a catalyst on a reaction. Here, this is our original path, and now we have catalyst indicated by the dashed lines. We can see that the peak is getting lowered, and at the same time the activation energy for both of the forward and backward reaction, they also get lowered. That's how the catalyst is able to speed up a reaction, by lowering the activation energy. And the one thing to note that even though it lowered the activation energy, the enthalpy change of the reaction has never changed. It starts at the same place, it also ends the same place still. So the change in enthalpy is not being affected by catalyst. Now let's continue to talk about reaction mechanism. And we talk about that reactions are basically collisions between molecules. We need to have both the correct orientation and sufficient energy for the reaction to take place. And let's talk about more exactly what is a reaction mechanism. Reaction mechanism is a series of elementary steps that's proposed during a chemical reaction. For example, you might see these chemical reactions, but in reality, the reaction is not simply like that. It's not happening in just one step. It has multiple steps, and then it reaches the final product indicated by the net reaction. And some steps are faster than the others, and what we call the slowest chemical step to be the rate determined step of the reactions. In this case, the first reaction step is the slowest, so that will be the rate determined steps. And also the rate determined steps contains the highest activation energy, and that's how we're gonna recognize it if we are given a graph. And let's see two types of questions where we need to find the rate determined step of a reaction. So the first type is we are given a reaction diagram. In this case, what we need to do is determine the activation energy for each step. So the bottoms or the chart of during the graph represent one state of the reactions, and in between the peak and the left side state, it has a activation energy. So we can see there's 1, 2, 3 peaks in total, and it corresponding to 3 different activation energy for each step. And we can see that the first step contains the highest activation energy. So the first step is going to be the rate determined step of the reaction. The second type of the question that we will be given to determine the rate determinant step is by having a series of chemical reaction steps. So that in this case is very easy. These type of questions are easy because you just need to find which one of them is the slowest. And that step is going to be your rate determinant step. Now let's talk a little bit more about rate law. Using chemical mechanism, we can also determine the rate law based on that. So here are the steps that we need to follow in order to determine the rate law. So the first step is determine the rate determinant step. We just need to find the slowest one. In this old example, we can see that step 2 is the slowest. So that one is going to be the rate determinant step. And then we will be writing the initial rate law based on our rate determinant step. So in this case, N2O2 times the concentration of H2 and times the rate constant K, we will have an initial rate law. But that's not our final answer, because recall that the definition of the rate law, we can only have the reactants that's in the net reaction to be inside our rate law. Anything that's other than that is not being accepted. But also the catalyst is acceptable in our rate law expression. So the problem here is that we need to find a way to replace N2O2. So according to something stupid, that's called equilibrium estimation, which states that in a fast equilibrium, the forward reaction and the backward reaction has the same rate speed. So what we need to do is that we first write the rate for the forward reaction and the rate for the backward reactions, and then we can find a way to replace N2O2. And just note that K could be just some kind of number, so it's just for simplicity. We just try to combine them together if we are trying to multiply them together into another K. So each K could represent a different value in reality. So now we have a new expression for N2O2, and we just sub in that into our initial rate law. We sub that in, and as I just mentioned before, that K just represents some kind of number, so we don't care. Just combine them into another new K, and we have our new rate law. And just check they are both our reactants inside our net reaction. Did I write the net reaction here? Okay, never mind, actually no. So that's how you're gonna determine the rate law for using a reaction mechanism that's being proposed. And let's try to do some examples. Maybe that will help us to understand this topic better. So still, first we determine the rate determinant steps, just finding the lowest one. And we obtain our initial rate law. And check if they are both our reactants of the net reaction or not. And we add those three reactions together and cancel out the same terms that are on both the reactant and the product sides, and we end up with our net reaction. So we can see that A, B are both our reactants, so there's no need for us to make any change to our initial rate law. And exercise number 3. So here we just do the same thing. We determine the rate determinant step, and then we write our initial rate law here, and we check and we write out our net reaction for the reaction mechanism, and we find that I square it's not one of our reactants, so we need to replace it. And using the equilibrium estimation, we find a expression that can be used to replace the I squared. So we sub that back into our initial rate expression, and we get our rate law. And another more complicated example. So we have 3 different complicated reaction mechanism steps. And note that D is a catalyst, so we may include that into our rate law. So we determine our rate determinant step to be number 2 because it's the slowest. And we write our initial rate expression. And we add those 3 reactions together and cancel out the terms. We get the net reactions. And then we check if our initial rate law are both containing only the reactants that from the net reaction. And we find that ACD is not one of our reactants, so we need to replace that. And using the equilibrium estimation, we develop a expression for ACD. Okay, and then we sub that in back to our initial rate law, and we get our final rate law. And D is our catalyst, even though it's not our reactants in the net reaction, but it's still acceptable. Now let's talk about integrated rate law. So integrated rate law allows us to predict how the initial rate of the reaction changes as the time goes on. And there's 3 different versions of patterns that you need to remember. You can continue to have more orders if you want, but that requires some basics of the calculus, and the AP exam will just stick with those 3, and it will never go beyond that. We have 0, first, and second order. So recall that these are the versions of our rate law for each order of the reaction, and if you integrate each 3, and you will get a brand new equations. And just do you an example, I will try to integrate the 0 order rate law over here. So we first change this k into negative because we want this k to be positive, but this rate is actually consuming the reactants. So we will flip the sign here and make it negative. And we put the dA over the left side and put dt on the other side. And we just integrate this differential equation. And recall that for a constant, if you integrate it, it's just the variable itself. And we got t, and don't forget the constant c over here. If we sub in t equals to 0, then this final concentration will just be the initial concentration. That's why this c is equivalent to the initial concentration. For the first order, we just do the same thing. Just don't forget that the integral of a 1 over something is ln something, okay? And if we sub in t equals to 0, and this thing over here is just going to be the initial concentration of log. And in the AP exam, you might be asked what kind of order of reaction it is basing on a graph. So for the 0 order, the concentration and the t has a direct relationship. It's proportional and having a negative slope. For the first order, the ln of the concentration and t has a direct relationship, and it has a negative slope. For the second order reactions, 1 over the concentration and the t, they have a direct relationship, and this is a positive slope. So in the exam, you might be asked to read a table and to determine what kind of reaction it is, what kind of order of the reaction it is. Just like this, you are given the concentration and you are given the time. So first thing first, we will be making a table of each time the value of these. Okay, for the second order is 1 over the concentration. For first order is long concentration. For zero order, it's just the concentration. We can quickly tell that this thing here is not zero order reaction because the slope is obviously not constant. Recall that the concentration and the T, they must have a linear relationship, but it's not the case over here. Okay, so if we want to tell if the reaction is between a first order or a second order, you need to create a table of these. But due to the time reason in the AP exam, you will just have three entry. You don't need to create a whole table like what I did over here, because just 3 will be enough. And I recommend you pick the first one, the middle one, and the end one, okay? Because it's much easier to reflect the change, and you'll only need to calculate these 3 times, which is the bare minimum that you require to determine 2 different slopes. So for the 1 over concentration, I picked the middle one and the initial concentration, and I take the slope. I picked 2 entries from here, and I divide by the difference of the time here, and I get the slope number 1. Similarly, I pick 2 entries from here. Okay, I pick 2 entries from here and divided by the difference of the time, and I get slope number 2. And you just do very similar things here, and pick 2 entry divided by the difference of time, pick 2 entry divided by the difference of time, and you get 2 different slope. And we will be comparing if each slope are actually the same. So this one is not that bad, it's just off by a little bit, and this one is kind of off by 2 times. So we will not be picking this one, so it's probably a second order reaction. And another thing that the AP exam could ask you to do is calculate the rate constant from the reactions table. So for the second order, we know that it's positively related to the 1 over concentration. So K is directly equals to the, it's just equals to the slope of the second order reaction rate constant. K is equals to the slope of the graph, sorry. And for the first order and the 0 order, K equals to the opposite of the slope. You just need to flip the sign, and you can calculate the K. And the third thing that the AP exam might asking you to do is that you will be given a random time, and using the rate law that you integrated rate law that you determined in the previous parts to calculate the concentration of the product. So in this case, we have a second order reaction, and we just use this equation, and we know our initial concentration, we sub in, and we already calculate the K from part B, and we sub in the time. We got this thing over here is equal to this value, and we flip it, and we can calculate the concentration of the product. Sorry, not the concentration of the product, the reactants, sorry, whatever. And now you know how to calculate the concentration. Let's talk about half-life. Half-life is the time that required to become the half of its initial value. It could be concentration or mass. The half-life for a first order reactions is constant. And here is the derivation. we substitute the half of the initial value to our final value, and we take out the log, and we cancel out the term, and we are left with this useful formula over here. And let's try one simple example. If a first order reaction has half-life of 20 minutes, find the rate constant. So using this formula, K equals to ln 2 over T half, and ln 2 divided by 20 minutes give us 0.035 minutes per minute, sorry. And part B, how much time is required to be 75% complete reaction? So that means that there's only 25% of the reactants being left, and this expression is the natural log, and 1 over 2 to the power of the time constant, and we just take the log of this and then times the 20, and this will give us the time that's being required, which is 40 minutes. And thank you for following me in this unit, and see you in the next one.